In this lesson, we're going to talk about bases for vector spaces. A basis is a set of vectors that's both linearly independent and also spans a particular vector space. So in some sense, it's a minimal set in which you can write all the vectors in your vector space as a linear combination. Now, there's more than one basis for any given vector space, so we need to keep that in mind. I have a simple example here. You may have seen this in calculus or maybe a basic physics course. We have an x, y, z axes in 3 dimensions, and then we have these unit vectors I, j, and k. We could have given them different names, but that's what you'll see a lot in physics. And the idea is that these 3 vectors form a basis for 3-dimensional space, and you can take any point. I have an example here, 2 minus 4, 8, and you can write it as a linear combination of these 3 vectors. So you can see here that we can write this vector here as 2i minus 4j plus 8k. And if you actually do these computations, you would come back to this vector here. So this is a special type of basis. It's called an orthonormal basis because they're at 90 degrees to each other. You can see here they're along the axes, but there's, in fact, not only are there multiple bases for R3, but there's also multiple orthonormal bases for R3. So we'll get to some of these concepts later on, but in this lecture, I just want to talk about the definition of a basis and then provide a few theorems. As I mentioned on the previous slide, and I'll repeat it here, a basis for a vector space is a set of vectors from the vector space that is linearly independent and that spans the space. Some definitions of basis will actually also talk about the order, and they'll say if you have the same set of vectors but they're in a different order, then you have a different basis, and that has some implication on how you represent other vectors in terms of the basis, but we'll get to that level of detail later. So for example, and this is basically the same example we talked about on the previous slide, 1, 0, 0, 0, 1, 0, 0, 0, 1 is a basis for R3, and then we can extend that to Rn, and we write that out here. We have 1 with all zeros, and then 1 in the second position, everything else 0, all the way up to n and 1 in the nth position. So that's called the standard basis. Sometimes I'll use this notation epsilon sub n. And the idea is you could take any vector in Rn, showing here v equals x1, x2, all the way up to xn. And then if you take x1 times e1, x2 times e2, all the way up to xn times en, and add it together, you get back to this vector here. A subset S of a vector space V is a basis if and only if each vector in V can be expressed uniquely as a linear combination of vectors in S. So we need to prove this in 2 directions. It's if and only if. Let's start by assuming S is a basis. By way of contradiction, assume there exists some V that can be represented 2 different ways as a linear combination of vectors in S. In other words, not uniquely. So we write V as this and then this. Subtracting the 2 expressions here, we get A1 minus B1S, A2 minus B2S2, all the way up to AN minus BN SN equals 0. Since the vectors of a basis are by definition linearly independent, it must be that each one of these coefficients is 0. In other words, A sub I equals B sub I for I equals 1 to n, and so the 2 representations are the same. So we weren't able to make the assumption that we started up out here that there were more than one way of representing a vector. So we have our theorem going in one direction. Going the other way, assume every vector in V can be represented uniquely as a linear combination of vectors in S. This implies S spans V. So we only need to prove that the vectors in S are linearly independent. Suppose there is a non-trivial linear dependence among the vectors in S, where at least one of the coefficients is not equal to 0. So I've written that out here. And there's some A sub I not equal to 0. But that gives us two different ways to represent the 0 vector. We can represent the 0 vector like this, where we have an AI that's not equal to 0. And then we could also represent the 0 vector where all of the coefficients of the vectors in S are set here are 0. So that contradicts the uniqueness part. So that can't be the case. And so the vectors in S must be linearly independent. In a vector space V with basis S, written out here, the representation of V, small v in V, with respect to S is the vector of coefficients used to express V as a linear combination of vectors in S. So in other words, if V can be written this way in terms of the vectors in S, then the representation of V with respect to S, which we write here in this format, you just pick off the coefficients and you put it in a row vector, and you put a little s here to emphasize you're using this basis. Or you could put it in column forms. Sometimes it's the same idea, but sometimes you need a column as opposed to a row. And this comes back to the representation issue I mentioned earlier about the order that you list your elements in the basis. So technically, if you switched S1 and S2, for example, then these representations would also change. You'd have A2 first and then A1. And so the order is important when you talk about representations of a vector in terms of a basis. Let's look at a few examples. First one is an R3, and here we have a different basis. I just multiplied the standard basis by 2, 3, and 4. This is still a basis. Then we can take a vector, for example, 2, 2, 2, and we can write it in terms of these three vectors. We can just take the first vector to give us the 2 here, and then the second one, we need a 2 again. So if we multiply this by 2/3, we'll go to 0, 2, 0. That'll give us a 2 in the second position. And the last one, we just need a 1/2 times the 4. That'll give us a 2. So this is one where you can kind of look at it and just compute it in your head. Normally you have to solve some equations, but this was kind of an easy one to just look at it and visually do the computation. And then when you want to write the vector 2, 2, 2, in terms of this basis here, it would be 1, 2/3, 1/2, and you put a little s here to emphasize that it's in terms of this basis. Then it's understood, you notice there's no little subscript here. It's understood that this is written in terms of the standard basis. So you'll see that a lot in books. They won't even bother to mention it, but that's the idea here, that this is written in terms of the standard basis for R3. Then for another example, we have the basis of all 2x2 matrices, or at least one example of a basis. And it's just the 1 in each of the different positions. So it's very similar to R4, except just the format is different here. It's a matrix. And then you can represent this vector here, 2, 3, 7, 1, is 2, 3, 7, and then 1. put a little m here to emphasize using this basis here that we've been given. Let S be a basis for a vector space V where S has n elements. Then the equation A1 V1 plus A2 V2 all the way up to AK VK equals 0 for vectors in V, K vectors in V, and the coefficients being real numbers. This holds true if and only if you take the same coefficients, but now you use the representation of these vectors, these K vectors, in terms of the basis S. So these would be, in this case, column vectors. So if we took the linear combination of these column vectors, that would also equal 0 if and only if this equals 0 and vice versa. So let's prove that on the next slide. I copied our theorem from the previous slide just so we can look at this statement. And basically it's saying we have a set of vectors V, K of them, and the linear combination equals 0 if and only if the linear combination using the same coefficients but representing the vectors V 1 to K using our basis S also equals the 0 vector. So we start by letting S be this set here, S1, S2 up to S sub n. This is our basis. And then we write each one of these vectors V sub I going from 1 to K in terms of the this basis here. So we needed double subscripts to do that, and I've shown V sub j, it equals C sub 1j times S1, C sub 2j times S2, all the way up to C sub nj times Sn. So this is the representation of V sub j in terms of the basis S. And I wrote it here as a column vector. I just took these coefficients and I put them in a row here. So we'll need to visualize this later on. That's why I'm writing it out like this. So if we start here, and these steps are going to go in both directions because of the, we need to prove if and only if here. So if this is true, if and only if, and that's what this little symbol means here, if and only if. If this is true, then it's true if and only if this is true here. And all I've done is taken the V sub 1, V sub 2, all up to V sub k and plugged in the representation here. So you have, when j is 1, you get C11, C21, so forth for this one. And then you go all the way up to k, get this here. And this is true if and only if. And all I've done going from here to here is I've collected everything that's multiplied times at S1. So all these terms are multiplied times S1, and you do the same for S2, all the way up to Sn. So these three statements are equivalent. This last statement here, we can write it out since the S is a basis, then a linear combination of the basis equals to 0 implies that each one of these is 0. So just this is 0. I didn't write the second one here, but that would be this one here. That's 0. And then the last one equals 0. So we have this set of equations, but you notice this is A1, and then this is just V1 going up vertically. This is V1, and then you'd have A2 times V2 and AK times the VK. So in other words, this is the same as this, just keeping in mind the structure here. And so each one of these statements goes in either direction, but we started with this and we ended with this, which is what we wanted to prove. Okay, so a little bit complicated, a lot of notation. You may need to stare at this a bit to identify this with this, and hopefully this will help you see that each one of these columns is one of the representations of the vectors v sub j in terms of the basis S. Let's look at an example of our theorem from the previous slide. We can take three vectors in R3, 1, 1, 1, 2, 2, 0, 0, 0, 2, and if we add them together using the coefficient minus 2, 1, and 1, we get 0. You notice we get a minus 2 from this first component, then a plus 2, and that gives us a 0. Then minus 2 and 2 again, we get 0. And then for the last one, we get minus 2. There's a 0 here, but this is a 2, so we get 0. And then we can use a basis, S. I've used this one here, 2, 0, 0, 0, 3, 0, 0, 0, 4. And what we want to show is that if we take, since we have this here, if we take these three vectors and represent them in terms of the basis S, then when we take the minus 2, 1, and 1 as the coefficients for the representations, we also get 0. So the first step is to write each one of these three vectors in terms of our basis. So the first one is 1, 1, 1 is we take 1/2 this, 1/3 this, 1/4 that. We're going to get 1, 1, 1, so that's the first one. Then to get the second vector, we take 1 times this plus 2/3. That'll give us a 2. And then we can just do 0 times the last term since we only needed the 2 and the 2 here. Then the last one's even easier. We just need to take 1/2 this third basis vector, and we get this here. So we get 0, 0, 1/2. And so if we take the minus 2, and then the 1, and then the 1, and add those together, just plugging in these values for the three representation vectors, we have this. We just take minus 2 times this one, and these two just have a 1, so we don't have any work to do here. Then we have minus 1 plus 1 plus 0 is 0, minus 2/3 plus 2/3 is 0, 0 here. Then we get minus 1/2, 0 plus 1/2, we get 0. So what we had in our theorem holds true here. Just one point to be made. If we're talking about R3, for example, then of course the basis has to have 3 elements in it, but the vectors that we add together to get 0, we could have had just 2 vectors or 4 vectors or 5 vectors. The theorem still holds. I just happened to pick 3 and show how they would be added together to get 0, but that's not required in the theorem. The theorem says you have k vectors v, and that k could be either less than or more than the number of vectors in your basis. Okay, so that's the last slide in this lesson. We still haven't actually proven that every basis for a vector space has the same number of elements. I may have almost implied that, but in fact that we need to prove that, and we'll talk about dimension and other similar concepts in the following lectures.